A very good morning to all of you. We present our heartfelt gratitude to Allah for gracing the occasion. And I have the privilege of introducing Dr. Pravita Kumar. She is professor at Department of Chemistry, Sri Aurobindo College at University of Delhi. She completed her PhD in 1998 from the University of Delhi on the topic physicochemical synthesis of metal complexes with semicarbazole and thiosemicarbazole. She has a teaching experience of more than 32 years and research experience of over 6 years. Her area of specialization include environmental chemistry, shift-based chemistry with transition metals, and green chemistry. She has published over 25 research publications and has delivered more than 100 life. She has delivered more than 100 live lectures on various topics in organic chemistry in this Swayam Prabha on Vyas channel, UGC Gurukul. You can also see her live lectures at webcast.gov.in. She has also published one book on physical and organic chemistry for undergraduates, published by Sri Kala Prakashan in 2019. She has been a part of several national and international conferences, workshops, seminars, and webinars, and has been a member of several professional bodies since more than 10 years, past 10 years. She is currently guiding two research scholars as a co-guide. Ma'am, we welcome you. Thank you. And the session is over to you, ma'am. Thank you so much. Okay. Thank you so much. It's okay. I think our guest, Professor Nand Kishore, is there, and it's my privilege to introduce Professor Nand Kishore. I welcome you, Professor Nand Kishore. Good morning, and also on behalf of winners and whole organizing team, I welcome you here in two-day international seminar, Current Trends in Chemistry for Sustainable Living. Professor Nand Kishore is currently professor in chemistry and Dean of Administrative Affairs at Indian Institute of Technology, Bombay. He was head of department from December 2008 to December 2011. He did his MSc in chemistry from Guru Nanak Dev University in 1983. After completing his PhD chemistry from IIT in 89, he received post 1991 and at the National Institute of Standards and Technology, USA 1991 to 1992. He joined as a faculty at IIT Bombay in 1992. He has been guest research scientist several times at the National Institute of Standard and Technology, USA afterwards. His research interests include understanding physical chemistry underlying the biologically important system. His research group has contributed to the thermodynamic characterization of protein folding, intermediate drug-protein interactions, protein-solvent interactions, prevention of aggregation or fibrillation of proteins and drug delivery system by using a combination of calorimetric and spectroscopic techniques. He has published about 150 papers in international journals of repute in areas of physical chemistry, biophysical chemistry, and biochemistry. He has delivered several plenary and invited speakers in national and international conferences. He is fellow of National Academy of Science. He was president of Indian Chemical Society, Mumbai, branch 2010 to 2012. And for contribution to research in physical chemistry by Indian Chemical Society. So I would like to invite uh, for sharing your insightful thoughts with us, our students.
Thank you, ma'am. I hope I am audible. Am I audible? Hello.
Hello, 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 hello,
Hello. Am I audible?
hello.
Hello. Am I audible?
Yes, Professor, you can continue.
Okay. I hope. Okay. Thank you. Thank you, ma'am, for kind words of introduction. Uh, just once again checking that I am audible. Please confirm.
You are audible to us.
Thank you. Thank you. So, first of all, I would like to thank the organizers of the conference, specifically Dr. Kanika and her team, for inviting me to share some of our research work on this particular platform. Uh, the conference is a very topic on current trends in chemical sciences in sustaining living, sustainable living. A lot of research which is going on in this direction, and I will today focus on what we have on, that is importance of identifying molecular modalities towards rational drug design and drug delivery. So, since we have been working on biologically important systems, specifically on proteins, so therefore, for me, it makes a sense to start with the what is protein folding problem, a problem which is still unresolved. 2023 or 2024, we still do not have a protein folding code, although the theoretical chemists, they claim that they can give you a code for the folding of small protein. Algorithms for accurate folding of small proteins may be available. So now we have more than 80,000 protein structures in protein data bank. We have good computational approaches, but we still do not have enough experimental evidences for various models which predict the protein. Why this protein folding problem is important, I will elaborate very briefly. When the protein is synthesized in the body from ribosomes, then it has to acquire a three-dimensional functional form. And in order to acquire this three-dimensional functional form, it has to go through various intermediate states. So therefore, understanding these intermediate structures or intermediate states becomes very, very important. Since I would like to specifically highlight the importance of the thermodynamics in this, and when we talk about thermodynamics, the role of calorimetry becomes very, very important. And when we talk about the calorimetry, there are two types of calorimetry. which have helped a lot in not only understanding the protein folding problem, but understanding the biologically important interactions which make a significant in understanding their function in deriving guidelines. So differential scanning calorimetry and calorimetry are tools which can give the information about the heat evolved or absorbed during any type of interactions. So what do we get out of these calorimetric techniques when we apply these diverse problems? The changes in thermodynamic signatures, for example, the change in Gibbs free energy, change in enthalpy, entropy, these not only are the number, but they give a lot of information about the role of functionality in molecule in particular type of interactions. So in drug delivery, discovery and drug development, the target identification, target validation, assay development, secondary screening, etc., right up to formulation are very important, where the industries have used calorimetry a lot at several stages of this drug discovery and development process. For example, sometimes it becomes also very important to understand the affinity of different isomers and enantiomers towards a target protein. So our group has been working on understanding this protein folding problem, understanding the protein folding states, and how to use these techniques in identifying the molecular functionality. For example, in drug discovery or drug development, in pharmaceutical areas, RO5 becomes very important. Without going into details, these 5 rules are molecular weight, number of hydrogen bonds, donors, number of hydrogen bonds acceptors, toxicity, and log P. P is the partitioning coefficient. That partitioning coefficient is actually directly related to hydrophobicity of the molecule. Oral bioavailability of any drug molecule depends upon its solubility and depends upon its membrane permeability. If we look at the prevalent approaches from synthetic chemists who are working towards new drug development, synthesis of new molecular entities, they will agree that prevalent approaches have resulted to more hydrophobic compounds. In fact, a survey suggests that out of 1% of drugs, only 5% of the new molecular entities, they fall into this category of high permeability and high solubility. Whereas 90% of the marketed drugs, they have either low permeability or they have low solubility. And this is a real big problem in pharmaceutical industries. So for sustainable living, for the drug development processes, along with the methodologies, as I just mentioned, that the thermodynamics of the processes, understanding thermodynamics of the processes has made a big impact. For example, if we just look at the thermodynamic signatures which are presented over here, these are the thermodynamic.
Hello? Sir, can you hear me?
What are the statins? The statins are cholesterol lowering drugs. And they have their action by interaction with the HMG CoA reductase. If you just look at the trend over here,
क्या आवाज आ रही है
the trend from the first in class of the drug to the best in class of the drug, if you
उन्होंने भी पूछा भी नहीं कि नहीं स्लाइड आवाज पूछा उन्होंने स्लाइड का पूछा ही नहीं मेरी स्लाइड आई नहीं है फोन नंबर है बस कॉल कर लो तुरंत करो
may I request others to please mute because a lot of sound is coming.
Sir, can you hear me? I'm from
Muted from this side.
Sir, I'm from Shamli College. Can you hear me?
We cannot see your screen.
So you cannot see my screen. Actually, what I'm getting is that host has disabled participants' screen sharing. Can you enable screen sharing? Then I can begin again. I'm not able to share the screen.
Now you can share your screen.
Can you see now? Can you see the screen now?
Visible.
Hello.
We are able to share the screen, but the PowerPoint is not visible.
Can you see the screen?
Yes, sir. Kindly switch on to the slideshow mode.
I cannot hear you. Can you please confirm? Can you see my screen?
Yes, sir, fine, sir.
Okay, so I'll just quickly recap what I just said. Yeah, okay, thank you. I'll just quickly recap, what I just said. That I was talking about I was talking about the use of calorimetry in our research, that the differential systemic calorimetry and isothermal titration calorimetry we have used in a big way. And then I was talking about this, that the thermodynamic signatures become very important when it comes to identifying molecular. And then I touched upon this, that the calorimetry means real applications from target identification right up to formulation. And then I was talking about the Lipinski rule of 5, and that is where we were in the previous part of the presentation. So I was talking about the molecular weight. I was talking about that no more than certain number of hydrogen bond donors and no more than certain number of hydrogen acceptors. And log P, which is the partitioning coefficient. These are the 5 mechanisms which becomes very important in rational drugs. Then I was talking about that out of 41% marketed drugs, only 5% fall into high permeability and high solubility quadrant, whereas 90% they fall into low permeability or low solubility quadrants. And these are the big problem in pharmaceutical industry. Therefore, a lot of effort goes in introducing polarity into the new molecular entities. As an example, the thermodynamic signatures associated with first in class of drug to the best in class of drugs for statins which are cholesterol lowering drugs. If we look at the trend for their interaction with HMG-CoA reductase, the green bars which represent are constantly increasing thermic interaction. So it is not that the scientists designed over a period of time that the new molecular entities should interact in a more exothermic manner, but that the interaction was more of exothermic manner. That means the polar interactions, introduction of polarity in the molecular makes a difference. For example, here, we can just see the effect of adding a methyl group, a single methyl group. What is the effect on the green bar? If we look at the green bar, the gain in the exothermic enthalpy is only by 0.68 kilojoules per mole. But whereas if you look at the value of Kd, that means there is a big jump in the value of Ka association constant by a factor of 9. So therefore, a lot of efforts go into the engineering of binding affinity in a new molecular entity. That means we have to worry about the resolvation when this molecule has to go and sit in a binding cavity. Lot of water molecules have to be removed from its immediate surrounding. That is desolvation. So desolvation has an enthalpic penalty, whereas when it sits into the binding cavity, it can form hydrogen bonds, it can establish van der Waals interactions, and that can compensate for the enthalpic penalty, which was as a result of desolvation effects. So all these go into engineering binding affinity. We can see the effect of this methyl group with the hydroxyl group and just see the gain, the exothermicity of interaction. That means introducing the polar interactions become very, very important. Introducing the polarity in a molecule becomes very, very important, but the polar groups should not be added at a place that leads to a lot of enthalpic penalty. So we worked for a long time on this engineering binding affinity in a drug molecule, and we were able to assign the thermodynamic signature, and the thermodynamic signature with the spectroscopic observations providing guidelines towards improving the molecular entities. As a recent work, we were interested in understanding what is the glycation of drug and transportability of human serum albumin. Human serum albumin is a major transport protein in our blood vessels. And its concentration in the blood is high. So therefore, if we look at its structure, it can carry a variety of drug molecules. So we wanted to understand that under diabetic conditions, when the glycation happens, does it affect the drug transportability of human serum albumin? So for this, we injected the protein for a period of 3 weeks under glycating conditions, and then we wanted to understand what happens from week 1 to week 4, and what are the these advanced glycation end products which are also produced along with as a result of glycation. So a lot of methods were applied, from absorption spectroscopy to fluorescence to NMR photometry, and we tried to understand that what are the various MOD products and glycation end products which are produced. But that is not my purpose of highlighting it over here. This is just a methodology of characterization of and their association with the human serum albumin. My interest was of showing thermodynamic signatures associated with the binding of diabetes-specific drugs and diabetes non-specific drugs. So for that, we chose two kind of drugs. One is naproxen and the other is pyridoxine. And if you look at data which is presented here in this table, the glycation from week 1 to week 2, week 3, week 4, if you see binding constant values do not change over a period of time. But the point which is worth noticing is the entropy change as a result of interaction. All the values are positive. And this positive means there is a lot of desolvation happening and the binding is reversed. We carried out the work with aminoguanidine, and with aminoguanidine also you see that the entropy change is positive. That means it is entropic. But if we look at the values of K, the K value is remaining almost even here with metformin. If you see, all the delta S values are positive, whereas the values of K, the binding constant, these values are not changing much, rather in some cases. So this is an important result. That means even after conditions, the drug transportability of serum albumin is not significantly affected. So then we try to further correlate with the binding ability of the drug for the open chain molecules or with the molecules which have the ring structure. And we observe that the open chain molecules are able to bind more effectively than the among the molecules studied which have the rings. But the most important result is to obtain the mechanistic insights, and in a nutshell, what I can describe over here, that amongst the drugs we studied, those drugs, their binding ability was not affected significantly, even under glycation. So now a little bit changing a different domain where the rational drug design towards coming up with the potential inhibitors for fibrillation or aggregation of proteins is concerned. We all understand that the fibrillation or the protein occurs as a result of either misfolding or deviation from the correct folding pathway. When the protein is synthesized from ribosome, it goes to the functional form, and then if it does not go to the functional form, it may deviate and go towards amyloid fibrils. And this formation of amyloid fibrils are the main reasons for various neurodegenerative diseases, Alzheimer's disease or Parkinson's disease. So what do we have in 2023 or 2024? We do not have a solution which can reverse this aggregation or fibrillation process. So a lot of research that this amyloid plaque which forms, it interferes with normal neuronal function, and that is why there is a need to have or work on obtaining the potential inhibitors of the protein aggregation or protein fibrillation. So the challenge lies in finding solution to inhibit the amyloid fibril and refold the protein to its. So, yeah. So how to address this problem? We employed the fluorescence spectroscopy, where high-frequency molecule and bind the fibrils fluorescence. So therefore, when the protein undergoes aggregation or fibrillation in its monomeric form, THT fluorescence can give us information on at what time the protein is in the monomeric form, goes elongation and undergoes mature fibrillation. Simultaneously, the imaging can be done for a complete characterization. So our approach was to interact the potential inhibitor with the protein at different stages of fibrillation process, and then understand that at what stage the potential inhibitor or inhibitor is able to reverse the process or is able to arrest the process or not. So this is the idea. You have native protein, you have protofibrils, and then you have the amyloid fibrils. These are the three stages of the protein fibrillation. We use the urea, and we also use these 5-fluorouracil anti-cancer drugs, and then try to whether the polar drugs can inhibit the fibrils, whether intramolecular bonds is formed between drug and beta strands. So what we did was we performed the fluorescence THT binding kinetics. We tried to understand, and then we observed that even at a later stage, that means not the early stages, the hydroxyurea of kind of molecule is able to inhibit fibrillation by 56%. 5-fluorouracil kind of molecule at the earlier stage 19%, and at the later stage. But this is characterization, but the thermodynamic signatures of interaction, if you see at the first stage, initial stage, 5-fluorouracil is able to go and sit at the periphery of and it is associated with an enthalpy of interaction of minus 69.5 kilojoules per mole. But when the beta strands start associating with each other, kind of molecules are able to interact or form hydrogen bonds, and that means they have potential to inhibit the association process, and they are not able to enter the already formed fibrils at the mature stage, simultaneously corroborated by the disappearance of the F90 or the peak in the F90 NMR. So these results clearly demonstrate the potential of these kind of molecules to inhibit the aggregation of fibrillation even when the from the nucleation to the intermediate states. Okay. Now, coming over to ionic liquids. The ionic liquids, they have been used a lot in organic synthesis, green chemistry, and we were interested in understanding whether liquids, they have biological applications and in what sense they can be effective towards this protein aggregation fibrillation. So amino acids based, these are we wanted to try because of the biocompatibility, and without going too much into details, what I want here is that this choline glycine, for example, this kind of amino acid based ionic liquids, you can see in the right side figures, the, the reduction in the THT emission is significant when the ionic liquids are introduced into the protein at the initial stages of stabilization process. That means, in addition to their protein stabilization ability, ionic liquids have great potential in prevention of degradation of the protein. So, these are just microscopic pictures showing that how, in the addition, by the addition of ionic liquids, this fibrillation or aggregation process prevented. Isothermal titration calorimetry finds significant application over here along with the differential scanning calorimetry, because differential scanning calorimetry will tell us that as a function of the time that the protein switches over from the nucleation phase along with how this enthalpy of transition varies, the stability of the protein varies. And the isothermal titration calorimetry gives information about the nature of interaction when these ionic liquids are added at the different stages of fibrillation. So, what we have here is now established that the ionic liquids have great potential not only in providing thermal stability of the protein, but also towards prevention in the aggregation and fibrillation of the protein, and more research should be dedicated towards that. Now, very briefly, I will not take too much time. I know that I have exceeded my time limit. So, very briefly, I want to touch upon the drug delivery aspects. That nowadays, as I said, that many drugs which have more hydrophobic character, their transportability to the target site becomes an issue. Even the membrane permeability is an issue. Therefore, variety of drug delivery systems have been tried. However, most of the studies have been dedicated towards qualitative understanding the drug encapsulation, but how to engineer the drug encapsulation ability and the release still remains a question. And for that, a thorough physical chemistry based understanding is required. So therefore, even if we start with the simple micelles which have hydrophobic core and hydrophobic core, we know that can trap the hydrophobic one. But when we switch over to neosomes, where we have different, their hydrophilic and hydrophobic areas where the drugs can penetrate or encapsulate, and subsequently the relationship of the functionality on the drug molecule and the functionality of the self-assemblies, that understanding becomes important. And in order to address that, we used the isothermal titration calorimetry and tried to demonstrate that the thermodynamic signatures have potential in suggesting the mechanism of interaction, mechanism of drug into the self-assemblies. For example, a combination of enthalpy of interaction and the binding constant can guide us in understanding where the drug is, whether it is able to enter the penetrate there or it is able to stay at the periphery of the molecule. And of course, one can also establish the structure property energetics correlation. What is the correlation between the structure of the drug, the molecular functionality, and the encapsulation or the binding constant or partition constant we are referring to the encapsulation ability. So therefore, the encapsulation of the drug and further its interaction with the target protein and how these drug delivery system affect the also becomes understanding that becomes important. A systematic variation in the molecular functionality and then its understanding of how these various functionalities or alterations affects the partitioning of drugs into the drug delivery systems. For example, here it is entrapment in the palisade layer. It becomes very, very important guidelines towards engineering the drug, not only the drug, but also the drug delivery systems. The profile studied by absorption spectroscopy can also be studied by isothermal typing, where not only it gives information about enthalpies, but also about the rate of release. And as I said, as the system becomes more and more complex, obtaining physical insight into where the drug is and where it will be more important. And where the of all these various techniques helps in obtaining insights and suggesting the suitable. Now, just last couple of slides, that variety of methods can be used to obtain thermodynamic signatures. One is direct calorimetry, and there are many other methods via spectroscopy. This information can be obtained. And what we observed is that when you obtain this thermodynamic signature, there are large discrepancies between direct calorimetry and fluorescence. So therefore, we try to come up with a protocol where these kind of discrepancies can be resolved. And if if someone is interested in looking at this article that appeared in Bulletin of Chemical Society of Japan. So here we have suggested a protocol where the discrepancies are from calorimetric methods and non-calorimetric methods be resolved. So what I have tried to cover in my presentation is that an understanding of the molecular functionality is very, very important when we want to establish how it will interact with the target protein, how it will encapsulate this drug delivery. And therefore, the thermodynamic signature, which directly carry the information on the nature of interaction, their understanding becomes very, very important. So therefore, a combined calorimetric and spectroscopic method enables an understanding of role of these biologically important systems. Biological applications of ionic liquids remain largely unexplored, and we are further working on this. And protein stabilization by a biological can offer in chemical and biological sectors. So with this, I would like to end my talk. Sorry for the initial glitch where I could not share my slides, but I hope that I'm able to convey what I want to do. With this, by thanking the financial support and my excellent PhD students, I would once again like to thank the organizers for giving me an opportunity to come over here and discuss with you, talk with you on this international platform. Thank you very much.
Thank you, Dr. Kishore. And it's an honor to hear you in a virtual mode as you have explained importance of identifying molecular functionalities of drug design which played a very important role in pharmaceutical industry. Also, how the drug-target interaction takes place, effect of glycation on drug transport ability. Also, you have explained in a very nice way for your proteins, as we know that drug design is a very inventive process of finding out the new medicines. So you have explained in a very nice way. And for because these types of discussions will very helpful for our audience because lots of students are sitting here hearing you. Definitely, they will benefit from this wonderful lecture. Thank you, Professor Nankishore.
Thank you, ma'am. If there are any questions, I will be glad to answer.
Sir, I would also like to add a bit thanking words on the behalf of the organizing committee of this conference. We thank you, sir, for following our schedule. Although we got to know that there was a president visit at your institution and you were also engaged there, but we are so thankful that you accepted our invitation and decided to write our students from your lecture. Thank you so much, sir.
Thank you, ma'am.
Good morning, Professor Naveen Future.
Yes, good morning.
Good morning, Professor Bhajan. This side, Dr. Pravita, and it's my honor to introduce you in front of my audience. I would like to introduce you, Professor Arun Bhajan, GCRC PG Department of Chemistry, Government Dingle College, Bikaner, is PhD from University of Delhi, and he has published more than 150 papers, 8 books, and 2 patents in his credit. Scientific students have completed their MPhil and also 20 students have completed their PhD under Professor Narendra Bojak guidance. He has delivered around 70 invited lectures in international and national conferences, including visits at Washington, D.C., USA, Abu Dhabi, Austria, and Nepal. He has organized around 50 conferences, workshops, symposiums. His majors are green chemistry, bioinorganic chemistry, and food and drug analysis. He has also contributed to innovation, science fairs, learning by doing projects, e-magazines, and a multi-faculty research journal. He has also worked on microwave technology for extraction, nanoparticle processing, and the development of low-cost green microwave biochemical reactions. In addition to this, he is also working on green auditing, anything, and augmented and virtual reality. He is the founder of BIRC, Bikaner Interdisciplinary Research Consortium, coordinator, ICAC, and member of the state level quality insurance cell. Welcome, you can continue your lecture.
Good morning, all of you. Am I audible?
Yeah, sure.
Okay. My PPT are visible and are these running? Just please check it. If these are not running, kindly inform me. Are these moving?
Right now, no.
Are they, yes, moving or not?
No.
Not moving.
Yeah.
Oh, so I'm doing it once again anyway. Is it moving now?
Sir, if you could switch to the slideshow, it will start moving. Right now, we can see your
No, now it's visible, huh?
but it's not a slideshow.
I hope that these are visible. If not visible, kindly inform me so that I can either restart or whatever methodology. I don't know. So, okay.
Right side. And on the left side, can be seen.
I'm not able to listen your voice. Is my voice is clear?
Yes, sir. Absolutely clear.
Okay, so green ceramics and their innovative application. This is the official topic for this presentation. Before I actually start it, I would like to convey my best wishes and regard to all organizers of this international conference from Shamlal College, including the Dr. Kanika Solanki and principals and other faculty members. For your convenience, I have divided this presentation into three portions, ideas and thought. If this slide is visible, this is another slide of ideas and thought, concepts and experiments, and our results and findings. 5 minutes I'll be taking for ideas and thoughts. Most of the time I'll be spending on concepts and experiments, and if time permits, I'll take 3-4 minutes for the future results, future work and results orientations. These are the top 10 areas. I think this slide is visible where we have shown the top 10 areas where the chemical science is interestingly working. And we are fortunate that after association and studying at University of Delhi, chemistry department, I could able to learn few things about the chemiluminescence and targeted protein degradation, which I have tried to apply at our institution. And at present, we are. हाँ. हाँ हाँ. अभी एक सेकंड, आप ऑनलाइन ही है तो मुझे ये बताइए, टॉप 10 एरिया वाला स्लाइड दिख रही है आपको?
Yes, absolutely. I can see your slide.
तो अब हमने इसको स्लाइड शो पे तो कर दिया है. व्हाट इज हैपनिंग? एक सेकंड, अब तो फर्स्ट आ गई होगी. ओके, मैं दोबारा से करता हूँ एक बार. एक सेकंड होल्ड रखिए. वैसे तो ये रन कर जाना चाहिए, नॉर्मली तो करता है. व्हाई इट्स हैपनिंग टुडे?
सर, हम आपकी सेकंड पीपीटी भी स्लाइड में देख पा रहे थे.
हाँ, अब देखिए आप एक बार. Is it moving? हाँ कर दिया. नहीं नहीं वो तो तरीका ठीक है, वो मैं कर लूंगा. आई एम आस्किंग दैट इज इट मूविंग और नॉट. No, then in that case it will not show the animation. Anyhow, I'll manage it. अगर बीच में स्लाइड मूव करना बंद कर जाए then kindly inform me. Okay. So now I think the top 10 area slide is visible.
Yes, yes.
Okay, fine. It will be perfect. So these are the area where we could able to work up to some extent. But due to these training at University of Delhi, we could able to develop this 11th area here. And this is the area of biosensitization in relation with the ceramics and other applications of composites too. And there, after doing lot of work on this, we could able to design few novelty and could able to file our fourth patent, which has been published recently. So actually in these 5 minutes, I would like to share few interesting points about the applications of different biocomposites, including the ceramic composites. So these are just questions in front of you, which is most hazardous. So normally we think about the plastic materials or like. So I would like to answer here because of shortage of time. Answer is the cigarette, because cigarette is having the plastic as well as it's having the nicotine. And second question is that related with the experimental learning. So which of the following is common in between following two pictures? So this is experimental learning because we are doing on the locational and dislocational advantages. So as you can find in the choice 3 and choice 4, choice 4 is very interesting here. The question is this, and answer is coming from the isoflavonoid, minerals, geochemistry, and anthraquinones. Interestingly, answer here is the isoflavonoid. And this is directly related with the ceramics, their applications, and the most polluted site, which is coming at the Delhi. Here you can find this is the ITO bridge, and this is the Mathura refineries, this is Everest. But the interesting is that our kitchens are most polluted one because of this formation of NOx. You know that above 780 degrees Celsius, when gas is coming out, atmospheric nitrogen and oxygen are reacting to form the different types of NOx, including the nitrous oxide, which is the major component for the world, which was the major component for the World War II hazardous material. Now, it is another interesting point is that which is most hazardous: asbestos, mold, radon, fire, electricity, VOCs, and lead. Most of the people may answer it for the radon, but interestingly, answer is the asbestos. If you are sitting in the seminar hall and you are having the false ceiling there, then that is made up of the asbestos. Where like I'm sitting here in the video conference room, so the false ceiling as well as because it's soundproof, so the sheets, the walls are also of the asbestos. Interestingly, that asbestos is containing traces of radon. So we are getting twin hazardous material like we were getting in the cigarette one. This is very interesting, which I would like to share with you, and you may be surprised to know that recently such article has been published in the Economic Times. The people from economics are working on this, and as a green chemistry person, we will have to think very seriously on these. Pill police required for. You can think for the answer. We'll discuss it later on if you will ask. This is one of the association India providing curriculum development, planning, assistant, etc. on chemical safety and related activities. And this is working for the curriculum designing as well as planning. And this is directly related with the ceramics, and the answer is coming from the area where I'm sitting. You must have heard about the Kalibanga, Hadappa, you must have heard Mohenjo-daro, you must have heard this. So this is the Kalibanga site where ancient ceramics, utilization of ancient ceramic, technology ceramics and other things related with the ceramics have been described, and lot of things are available there. If you get a chance to visit Bikaner area, then it's nearby Bikaner, around 180 kilometers, and that has been our source of inspiration, because of many materials have been observed in terms of, like, you can find it here, and these are having the different types of utensils and applied materials also. So now come to the point that at present we are having the quality glasses, sanitary materials, insulators, engine component, brake discs, high quality bridges, all are made up of the ceramics and related material. But the recent uses of the ceramics are in the dentistry. You must be knowing it, but artificial bones nowadays, instead of steel rods and screws, now artificial bones and screws are designed with respect to a different peculiar types of ceramic materials, and now the strength of these materials has exceeded to silicon carbide, norboride, and also find uses in the robotics too. So this is all coming from the one of our work is coming from the biosensitization of zinc oxide, that is related with the insertion, as I discussed earlier. So I'll be detailing it in a different way. Biosensitized zinc oxide we prepared and utilized it in the ceramic catalyzation, and normal zinc oxide was also prepared. These are the few results. I'm not going to discuss the results of this particular experiment, but I would like to show you this design which we have utilized for the preparation of ceramic based catalyst. And we have also designed the experiments related with the electrochemical panels. So this is the idea and thought. When you people are talking about the environmental issues, the most of the significant environmental issue is coming related with the global warming due to the escaping of carbon dioxide, carbon monoxide, etc. So our hydrocarbons are being converted into carbon dioxide, but people since a long are thinking on the reversal of this particular reaction. So what was the idea? So this is the idea. If the gas, carbon dioxide coming from the refineries, from industries, and even from your vehicle, coming as the carbon dioxide, which is hazardous material, if we could able to develop green catalytical converter, people are working on it since long, then that can directly be converted by using this ceramics based green catalytical converter into CNG or in the methyl alcohol. So we initiated some work after finding a lot of literature from here, and we before that we could able to identify our problems. You know that if we could able to design such green catalytical converter and just apply at the fuel engine of our releasing engine of our vehicle, maybe the bike or the car, so that catalytical converter there itself can convert that carbon dioxide into CNG or methyl alcohol in a very less amount. Once we get the substantial amounts, and then that catalytical converter is useful not only at the larger scale but at the smaller scale also, so that carbon dioxide can be converted directly into the CNG, methane, or methyl alcohol. So we initiated this thought to convert that carbon dioxide into the methyl alcohol. So what was the problems of micronization? I'm very happy that in the previous lecture, Professor Nand Kishore ji has explained you very well the effect of the micellization technique and neomicelles, neosomic approaches. So that knowledge of physical chemistry is directly significantly useful for the ceramic catalytical preparations. So materials which we are using here, the plastics, not the plastic, but the composites of the plastics, and then the extraction, solvents, stabilizers, and then the technology. But what are the problems? So four problems which we could able to identify here: the carbon dioxide hazards, solvent for extraction and synthesis, base material for binding, and material for immobilization. So the problems related with the or hazards related with the rising level of carbon dioxide leads to warmer condition but ripe atmosphere for the creation of particles carcinogen, as well as for the creation of smoke forming ozones. These are already known. But the problems related with the normal extraction, because we will be using three types of materials here. One is the composite based plastic, other the biocomposites, and other is the हाँ, कौन सा? एक सिंह दोबारा बोलिए, कौन सी वाली? आवाज भी नहीं आ रही। अच्छा, इससे पिछले कौन सी विजुअल थी? ओ माय गॉड, तो ये तो मेजर तो लॉस हो गया ना। इसीलिए मैंने आपसे कहा था कि प्लीज टेल मी, बिकॉज नाउ दिस स्लाइड इज विजिबल, ओरिजिन एंड थीम ऑफ द रिसर्च प्रॉब्लम। So it means your slideshow is not working there. Anyway, I'll move by this way. This is the most important slide. Anyway, I repeat it for a while. I'll repeat it. No, that is related with me. If slides are coming, then it's okay. Because I am on the election duty and I'm speaking from there itself. Anyway, chalo, I'll speak. Is it visible now? I hope that this.
Visible, sir. Your visible slides are also visible.
Okay. So this was the most important slide of my presentation. I'm just repeating it. The idea is that this carbon dioxide, which is coming from the different sources, maybe from your vehicle, our motive is to convert it into the methyl alcohol or methane or in the CNG by using such type of green catalytical converter. So in the next 5-10 minutes, I would like to explain you the preparation of green catalytical converter. So problems of micelizations are there, problems of carbon dioxide hazards are there, which I have already spoken, but the problems related with the extraction, because we will be using the 4 steps here. And all these steps where normal extraction process, the industries and even we are claiming that we are not using the chlorinated toxic solvents, we are using just ethyl alcohol or acetone type material. But interestingly, more than 2000 commonly used chemicals and Indian Pollution Board have also categorized this into the 4 grades. Grade 4 is the explosive material, and all these industries, including the ceramics, semiconductors, and computer chip industries, are using these solvents also. This is another important slide, which I have total 3 slides to discuss with you in detail. One I have already discussed. This is the second one. Again, the problem is of animation, but I would like to explain you from here itself. We are saying that industrial units are claiming that they are not using the alcohol or acetonic solvent, but using the chlorinated solvent, which is also the recycled. So when there is a solvent loss, say you are using the ethyl alcohol or acetone, then some amount is going in the atmosphere. Because 30% loss is normally there. And once it reaches at the site of the cloud formation, then after the showering, during the showering with water, some ethyl alcohol also comes out. And that ethyl alcohol or acetone goes into the underground water or in the surface water. Here the story starts. In the PWD supply centers. In PWD waterworks supply center, what happens? That water is stored in the big containers and the chlorine bleaching agents are passed. What are the purpose of the passing chlorine gas here? That acts as the insecticide or the purifying agent and kills the bacteria, fungi like materials. So ethyl alcohol is also there. Now just remember your 12th class chemistry. Ethyl alcohol, when comes in contact of chlorine in the presence of basic medium, a famous haloform reaction takes place and there is the formation of monochloroacetone, dichloroacetone, trichloro, and finally there is chloroform. Interestingly, the industry which was claiming that they are not using the toxic chlorinated solvent, knowingly or unknowingly, we are getting instead of alcohol like materials, we are getting chloroform in our drinking waterworks supply center waters, and that water is chloroform cannot be even detected. Purification RO methodology is far more away, and even no RO can purify such kind of traces of chloroform from here. So from these discussions, we could able to identify 4 problems for the preparation of green catalytical converter. One is the carbon dioxide hazards. other is the solvent extraction, third is the base material, and fourth is the material for immobilization. You all are from chemistry, so you can identify and you can think a proper protocolic solution for this. For the carbon dioxide hazard, as I said, that idea for conversion trans-esterification is there. Then the solvent extraction, as Professor Nandkishore was describing, the utilization of micellar system. So instead of the normal micelles, we have utilized here the green micellar system for the extraction. And then the base material for binding, that is very important. So we have utilized the Calotropis procera and 12 other wasteland desert plants here. Then the material for immobilization. Ceramics, if incorporated with neodymium, it provides remarkable results. How it happens, that is what I'm going to explain you. Now, in the next 3-4 minutes, I'll be trying to explain you the use of the neodymium and why we have used the neodymium here. From the literature, 5 things we could able to observe. And after observations of these 5 things, we started experiments after making one hypothesis: lanthanides are good catalysts if used selectively. That was very good. And that was very good paper in inorganic chemistry, and that was our result. So when we could able to prepare neodymium complexes, instead of 3 to 7 peaks in the hypersensitive zone, we could able to 3 to 7 or 10 peaks in normal conditions. We could able to identify 17 peaks, and in few cases 27 peaks. So that is directly related with the chemiluminescence and also with the biochemical luminescence activities, and that absorbance intensity provides a working station for the adsorbed neodymium type materials. So how it has happened? So that is related with the green extraction technique. You all know that there are the surfactants, ionic, cationic, and neutral surfactants are there. And then you are also knowing about the different types of micelles. So we could able to identify 2 types of micelles. One is the reverse micelle for the preparation of the neodymium complexes and their chemiluminescence in enhanced properties, and other is this rod shaped micelle for the extraction of the fiber that is basically lignin free fiber, that is the around 99% cellulose fiber from this Calotropis procera type materials. Interestingly, when we were performing the experiments on the extraction of the Calotropis procera material and the micellization of the neodymium catalyst material, we could able to get side product as a result of the bioluminescence. So that costed us the addition in our technology, and that decided as the value added incorporation. As you can find here, this micellization, this beautiful micellization not only increased the solubility and stability of the system for the neodymium and other materials, but a marked increase in the absorbance intensity was also observed. So that leads us for the nanoscale extraction. For the isoflavonoid and flavonoids, you know that the this discrimination is very little, so that can be extracted selectively. So we also started working on these, and we could able to extract this. So finally, by knowing these 4 factors, we could able to design several sets of experiments. I cannot go in the detail of all these experiments. It will take a long time, but I can just summarize that for the preparation of this green catalytical converter, we synthesized 32 complexes of the neodymium in a series, and then solution studies of these 32 complexes with different effects we could able to carry out. And then out of these 17 to 27 peak criteria to be taken in the hypersensitive zone, and then the potential complexes was selected. That was around 3, and then the synthesis of basic ingredients for catalytical converter was finalized. But that was mainly based on the 4 types of parameters. What are the 4 types of parameters that I would like to explain you? Before that slide, you can find that this is the lignin-free composite base composite material, and these are the 17 to 27 peaks, and this is the process of extraction. Because of the loss of animation in this presentation, I cannot explain you this. This is the animated video, and you can, this is self-explanatory. You can find that how this base material is prepared with the micellization technique. This is the representation of the rod shaped micelles. So now these are the different parameters when we are designing our catalytical converter, particularly on the basis of chemiluminescence. These are the parameters where we will have to study. So, or for all these 32 complexes and their systems, we could able to identify all these physical parameters. And these are the maximum and minimum values of the different spectral parameters. You can find the energy criteria in this case, that is the neodymium thiosemicarbazole 1 was essentially significant. And then in case of the doped one, we could able to calculate the RMS deviation for the Joule as per the applicability of the Joule-Dirichlet theory, and also the stereo environment around neodymium third ion, because that becomes the most significant part. So by the combination of knowledge from the literature, experimental observation made by researcher, interdisciplinary discussions with respect to above observation, this hypothesis was assumed that is the neodymium incorporated ceramic based catalyst can provide the better results. Now this is another slide, which is the third one. As I said you initially that 3 slides are most significant because these are the most original experimental patentable work. Patentable means we have already patentized these. So this is the green preparation of a neodymium based catalytical converter. Since again the problem is of animation, so I'm just telling you from here. Once the solution of neodymium complex is prepared, the problem is that how can we prepare a base material. So base material was prepared in the gel formation with the use of reverse micelles. But the second problem was that how the base material can be used as the binding material with respect to ceramics. So that in that condition, the lignin-free high tensile strength Calotropis procera based cellulolignic materials was used, and that was extracted from the Calotropis procera. And after that calcination was performed, so that a neodymium base ceramic catalytical converter, which is having the high value of the chemiluminescence and biochemical luminescence, so that can be utilized for the preparation of the methyl alcohol as well as methane from the carbon dioxide. And these are the X-ray analysis, and these are the different types of effects, because you know that effect of pH is very important, so as the composition. So finally we could able to get the better value of the heat evolved with respect to the glass transition temperature. And then we also went for the SCM studies and also for the catalytical behavior of these nanoparticles. So finally, if I come to the conclusion, I can speak out 2 things. In case of few neodymium complexes, 17 to 27 peaks have been observed in the micellar system. So only those 3 complexes were selected which were having the 27 peaks. And due to this, the efficiency of converting carbon dioxide into methane by our method is 4.5% only. But the literature is most of the literature is reporting 3 to 3.8%. However, nowadays people are working significantly for this. So we are trying to improve it further. Significance is that we are having the Joule-Dirichlet parameters, and T4 by T2 values are indicative of most identical system. Uniqueness in this work is that first time we have reported the neodymium micellar system with the 27 peaks. So this is the findings related with the future work, development of mechanisms of micellar isolation, effect of different surfactant is to be taken so that a catalytical converter can be prepared, which is having the conversion rate above 5.2%. At present, we are having the 5.2 to 6%, but recently we could able to find the another source material based on the neodymium templates. So that still working on this. So these are the few examples from the work. Future work, and instead of the isoflavone, such type of materials can be used for the biosensitization. I would like to stop it from here. I can just show one example. Okay, I'll leave here. I would like to convey all my best wishes in regard to all of these, so that due to these I could able to work up to some extent here, and definitely to our these collaborators. With them we are getting the financial supports, and also for the analytical applications free of cost. And this is the future work where we have just initiated just 6 months before for the molecular imaging using the ceramic based material, and neodymium has shown again another significant importance for this. And we are still looking for better collaborators in these area, particularly for the nano fabrications. These are the few papers which has been published, and I would like to convey again my thanks to all of these from Delhi University. It is always a pleasure to present something in front of persons from Delhi University. Thanks a lot. If you find any question query, I would like to answer. I hope that I have tried to compile it within 30 minutes or so. Thank you.
Thank you, Professor Bhagat, for sharing your thoughtful knowledge with us on green ceramics and their innovative applications. As you explained in a very easy way, like top 10 areas, and as you told us how those are the high performance, environmentally safe biocomposites. And also you explained, share your knowledge with us about the green converter, catalytical converter, micellar technology for extraction, and about this, the chemical sciences play a very important role for the sustainable development, and the sustainable future requires radical transformation how chemistry is designed, developed, and made. And here the topic was this line. Professor Bhagat.
Thank you. I would like to add only one point here, that I have raised one question there in the beginning that is related with the pill policing. I hope that in your this seminar, if you would like to take some aspects on this, so later on Shamlal College can also collaborate for this, and this is one of the very interesting topic as well as very recent one. Thank you very much.
Thank you, sir. I, Dr. Kanika Solanki, on the behalf of entire chemistry department of Shamlal College, University of Delhi, thanking you. We know that you are extremely busy in the monitoring of first phase election of Lok Sabha in Rajasthan. My words always fall short when I want to express my gratitude towards you, because you are mentor, guide, and a father figure for me. Thank you, sir.
Thank you very much. I am really sorry that this is the high peak time in Rajasthan for election point, and we all are busy there, but due to affection of Delhi University and all these, thank you very much. Thanks a lot.
Welcome, Professor Toshifumi.
Yes, I am here.
It's my honor to invite you and also share your CV to among with our all attendees. Professor Toshifumi Bohi is Professor and Deputy Dean, College of Pharmaceutical Sciences at Rex McKay University. He did his BS, MS and PhD from Osaka University. He has a teaching career of over 19 years He has several awards to his credit, such as the Pharmaceutical Society of Japan PS3 Award for Young Scientists, Bangalore Chemist Award, BCA Thane Chemistry Journal Award, Green Sustainable Chemistry, also Internet Award, Japan Association for Chemical Innovation, and Thane Chemistry Journal Award. Recently, he has been recognized with International Congress on Power and Applied Chemistry lecture awards and selected amongst world's top 2% scientists by Stanford University and elsewhere. He has published various prestigious research articles in International Journal of Repute. So I will invite you for sharing your thoughtful knowledge with us.
Okay, so can you hear me?
Yes, we can hear you. Apparently, we can hear you.
And my screen is visible?
Yeah, sure.
No problem? You can see this screen?
We can clearly see your presentation.
Mm. Okay, please check my comment. I leave comments. No.
Yes, we can see you. Yes, sir, we can see you. And now your screen is not visible. Probably you have stopped sharing the screen. So please share your screen, sir, so we can see your screen. And you are perfectly audible.
Okay, so please check my comments from the chat page.
Okay. Comments में चलिए.
Because I can hardly catch your voice.
क्या कह रहे हैं? Are you able to listen to me? Hello, sir. Hello.
Hello.
Am I audible to you, sir?
Good afternoon, Professor Doi.
Yes.
Good afternoon. You are welcome
Yes.
to Shambhala College.
Yes.
And,
Okay.
I request you may start your presentation.
Okay. So can you hear
you are
me?
welcome. On behalf of the organizing committee, I am inviting you.
Okay. Can you catch my voice?
Yeah.
Okay.
It's perfectly clear.
Okay.
You can share your
I will start.
presentation.
I will start this.
Welcome, Professor.
Yes.
Yes, Professor, your screen is visible.
Okay.
It's good to see you in this conference.
Visible?
Yeah, visible.
Okay. It's okay?
Yeah, it's perfectly okay.
Okay.
Again, you are welcome. You may please.
Yes. Okay. Oh, thank you. Thank you for Chairperson, for introducing me. Also, I'd like to extend my thanks to Professor Sranki and the members of the organizing committee for coordinating my lecture at this esteemed conference. Ladies and gentlemen, namaste. I'm a professor of chemistry at Ritsumeikan University in Japan. Today, I'd like to discuss our progress in metal-free coupling reactions by hypervalent iodine activation of aromatic rings, from pioneering findings to recent study in heteroatom couplings. Okay. This is today's topic, and following brief introduction, I will discuss recent research on heteroatom relations using these diaryl iodine salts. I believe you'll have the opportunity to receive a lecture on fundamental hypervalent in chemistry in India at some place. So I will begin with a brief overview of the hypervalent iodine reagent. These commercially available hypervalent iodine compounds, phenyliodine diacetate and phenyliodine bisulforoacetate, are useful in organic synthesis. They act as oxidizing reagent in reactions, and trivalent hypervalent iodine compounds are also used as reactive pursuit halides, and diaryl iodine salts are variable aerating reagent in both metal-catalyzed and metal-free coupling reactions. Additionally, desmatching periodinum and alto-iodoxybenzoic acid are useful oxidizing reagents for alcohols in the synthesis of complex molecules. The advantage of using these hypervalent iodine compound as oxidant is they are greener than metal oxidant due to their low toxicity, high stability, safety, and ease of availability. There are several important and widely used hypervalent iodine reagents and transformations, including PIDA and PIFA, which are commonly used in phenolic oxidation. In the 1980s, Professor Kita reported on phenolic oxidation using these reagents. The mechanism of the reaction involves the attack of phenolic oxygen on the iodine center, followed by the introduction of oxygen, nitrogen, and carbon nucleophiles at the par position, with the elimination of iodobenzene serving as the driving force. As a result of this process, de-aromatization occurs and spiral dienone was successfully synthesized. This reaction, which involves ligand exchange and elimination of iodobenzene, demonstrates the typical working mode of hypervalent iodine reagent. The use of hypervalent iodine reagents can be catalytically employed by generating reactive hypervalent iodine species in situ in the presence of the substrates. This can be achieved by using suitable co-oxidant that doesn't cause oxidation of the substrates. An effective co-oxidant is MCPBA and other per acid. These co-oxidants can generate active hypervalent iodine species at room temperature, and the use of a small amount of iodine can result in efficient catalytic reactions. This catalytic strategy is applicable for various de-aromatization reactions, including natural product synthesis and asymmetric transformations. More information can be found in our recent collaborative review published in Chemistry Asian Journal. Okay. The next slide is the field of hypervalent ion chemistry has experienced significant growth due to continuous synthetic breakthroughs. This is evidenced by the increasing number of literature publications on the subject. Hypervalent ion catalysis and asymmetric organocatalysis in oxidative transformations have been the driving force behind this growth in this century. Additionally, the use of hypervalent ion reagent in transition metal-free coupling reaction and oxidative cross-coupling reaction has also made significant contribution to the field. These advancements have enabled the construction of complex molecules through carbon-carbon and carbon heteroatom bond formation between two organic molecules. Regarding hypervalent ion-mediated coupling chemistry, my research group has pioneered for the first example of cross-coupling of two aromatic molecules. One of the key approaches in the production of fine chemical is a coupling reaction between aromatic compound and nucleophiles. This bar chart illustrates the synthetic method utilized in medicinal chemistry within a certain company, and it is evident palladium-catalyzed coupling reactions are frequently employed. The Negishi, Suzuki, and Bach-Bart-Hartwig couplings are effective in introducing a range of nucleophilic molecules onto aromatic rings. These transition metal catalysts play a significant role in various scientific fields. On the other hand, pharmaceutical compounds and organic materials sometimes necessitate high purity, and even trace amounts of metal species can be viewed as a problem. Consequently, a metal-free alternative method that can broaden the scope of coupling product is still needed in modern organic chemistry. In theory, the most direct approach for constructing carbon-carbon bond is oxidative coupling, which involves utilizing two CH bonds in each coupling molecules. Fanu reported on the palladium-catalyzed oxidative cross-coupling of heteroaromatic compounds, such as indoles and pyrols, using a metal co-oxidant. The products were typically obtained as a mixture of regioisomers by reacting indole with two CH bonds. Additionally, we accomplished for the first time a metal-free oxidative coupling of two different non-functionalized aromatic molecules, producing biallyls based on new strategies and concepts using hypervalent iodine reagent. Here, generation of aromatic cation radical would occur through the single electron transfer oxidation of this naphthalene aromatic ring. We propose our oxidative cross-coupling process begin with the formation of the naphthalene cation radical, which is generated through selective CT complex formation between naphthalene and PIFA. Naphthalene is more reactive towards the oxidant due to its lower oxidation potential than methylene. In order for this process to be successful, it is necessary for the smooth and selective activation of naphthalene over methylene to occur first, followed by the effective trapping of naphthalene cation radicals by methylene. Otherwise, formation of homodimer would occur. Additionally, high nucleophilicity of methylene allows for the efficient trapping of this naphthalene cation radical. And finally, over-oxidation of the biallyl product will not occur due to the steric hindrance that prevents CT complex formation of the product. Professor Kitter discovered in the 1990s, a specific hypervalent iodine reagent could cause single electron transfer oxidation of electron-rich aromatic rings. He also studied the reactivity of generated aromatic cation radicals with various nucleophiles. And approximately 15 years later, this discovery led to the development of metal-free cross-couplings. The use of hypervalent iodine coupling has been expanded to introduce the formation of biaryls between nacetals and a series of aromatic molecules. In addition, heteroaromatic compounds such as thiophene, pyrols, indoles, and pyridine derivatives are found to be effective in cross-coupling with each other and with other combinations. However, the reaction mechanism significantly differs in the case of these heteroaromatic compounds, as the heteroaromatic cation radical easily cause dimerization to homodimers and even oligomers. For instance, when thiophene reacts with PIFA or these causal reagents, followed by treatment with dimethylbenzene and trimethylsilyl bromide, this reaction exclusively yields cross-coupling product in good yield. This reaction proceeds through the formation of a thiophene iodine salt as an intermediate by dehydrative condensation of thiophene with a hypervalent iodine reagent. The bromide ligands derived from trimethylsilyl bromide is more favorable for the subsequent coupling with dimethylbenzene. This step constitutes a formal aromatic substitution, where the phenyl iodide bromide groups act as an exceptional leaving group compared to the usual iodine group. Our recent research has been motivated by these new findings, and we have shifted our focus to exploring diaryl iodine salts for transition metal-free hypervalent iodine couplings in heteroatom bond-forming reactions. In particular, we have found iodine salts containing a TMP group are highly effective as aryl group transfer reagents for a variety of nucleophiles. Diaryl iodine salt is a type of hypervalent iodine compound that has two aryl groups and one anionic ligand. The aryl iodide group in diaryl iodine salt is a highly effective leaving group, and these salts can react smoothly with nucleophiles in the absence of transition metal catalysts to produce coupling product. A groundbreaking study on metal-free coupling reaction using diaryl iodine salt was reported by Beringer, in which the reaction of phenol with these iodine salts resulted in the production of diaryl ethers in moderate yield. Despite the uniqueness of this metal-free coupling report, it failed to garner much attention, as the reaction of these salts with two different types of aryl groups should produce a mixture of two diaryl ethers. So, more than half a century after Beringer's report, Olofsson group revisited the metal-free coupling reaction involving diaryl iodine salts. They managed to enhance the product yield by fine-tuning of the solvents, base, and counteranion of the iodine salts. As an outcome, a broad range of phenols and carboxylic acid underwent O-allylation under milder metal-free conditions, resulting in high-yield product. These findings prompted many researchers to expand the scope of this metal-free diaryl iodine coupling strategy to include other oxygen, nitrogen, sulfur, and other nucleophiles. Following the publication of Orison reports, Gaunt proposed fluoride salts is a more reactive aerating agent. Furthermore, Olofsson, Stewart, and our group independently reported the use of TMP iodine salt as a selective aryl transfer reagent for metal-free coupling reactions. Moving forward, we will recently more focus on TMP iodine salts with acetate ligand to enhance reactivity, expand chemoselectivity, and broaden functional group availability during coupling reaction. Preparation of TMP iodine acetate is a simple and efficient process using our method. By treating various aryl iodide with green and cost-effective oxidant like peracetic acid, we can prepare hypervalent iodine compounds in the form of diacetate. These diacetates can then be directly reacted with TMP group to produce the desired TMP acetate in good yield. The distance can be okay. So X-ray structure of TMP phenyl acetate shows a secondary interaction between the oxygen group of TMP and the hypervalent iodine atom. According to the structure, the acetate should be located trans to these TMP groups. Additionally, the bond distance between the acetate ligand and iodine atom is shorter than the sum of their van der Waals study. The reactivity of diaryl iodine salt was investigated for the annihilation of naphthol. The torreflate and chloride salts were unreactive under these conditions without the presence of a base, while fluoride and acetate salts gave coupling product, albeit in low yield. Interestingly, all annihilation product was selectively obtained using iodinium acetate. This yield was further improved to 82% through a synergistic effect with the TMP group and acetate ligands. This reaction occurred without the need for a base, indicating the acetate ligand assisted by TMP promotes the deprotonation of naphthol. And when sodium carbonate was added to quench the acetic acid released during the reaction, the highest yield of the coupling product was obtained. You can see this process of annihilation using TMP iodine acetate involves extremely mild conditions for a wide range of phenols and aryl groups. For instance, product with electron donating and electron withdrawing substituents can be produced with over 90% yields. Even with bromine and other functional groups like aliphatic alcohols, aldehyde, ester, amines, and boronic esters, corresponding diaryl ethers can be obtained in high yield without any negative effect on these functionalities. In comparison to other methods that yielded the product in up to 52% yield, our reaction system, utilizing TMP iodine acetate, demonstrated a more efficient synthesis of the sterically bulky tetrasubstituted diaryl ether. Also, the reaction can be scaled up to gram levels, and after removing the solvents, TMP iodide can be removed as a solid by simple filtration. TMP iodine acetate for metal-free annihilation was also effective in annihilation of alkoxy-amines at a slightly higher temperature in toluene. A range of sulfonyl groups were available, leading to the successful synthesis of N-tosyloaniline, N-methylanilines, and benzene sulfonyl anilines in good yields. Furthermore, a variety of hydroxyamine with different protecting groups such as BOC, CBZ, TROC, benzoxy, siloxy, and isoxy groups were applicable for the reaction. Our coupling strategy allowed for the synthesis of this unique heterocyclic compound using the obtained anthoronic acid as an intermediate. So sulfone amides and carbamates gave N-allation product by reacting with TMP adenine acetate. Meanwhile, reaction of benzoamides under the same reaction conditions switch the product to this O-allyl imitate. The bulky tertiary redox groups at amide oxygen not only show the highest reactivity, but also increase the O-allylation. Tuning the steric and electronic property of amides and allyl groups of TMP adenine salts resulted in the perfect O-selective allylations. The presence of a methyl substituent at the also position of adenine salt was found to yield O-allylation product exclusively. This steric effect was not limited to adenine salts, but was also observed in benzoamide, as demonstrated in this example. Electron-deficient benzoamides and pyrrolidine amides exclusively produce O-allyl immediate products. Additionally, O-selective allylation was achieved even with N-methoxyamides for these substrate combination. Here, possible pathway for allylation is summarized. In general, N-alkoxy-benzoamides exist in two tautomers, and ligand exchange with the acetate anion of the adenine salts occurs. Coordination to the oxygen atom appears to be more favorable than that to the sterically hindered nitrogen centers, and secondary interaction with the hyperbonded iodine atom likely stabilize the immediate home, and these cause ligand coupling to produce O-allyl imitates. Alternatively, the formation of O-allyl imitate via ipso attack of amide oxygen in this iodine amidate is possible. The TMP group served as a unique ligand to promote the O-allylation process. Indeed, diphenyliodinium acetate decreases both product yield and O-selectivity. One possible explanation for the effect of TMP is the also methoxy groups of TMP coordinate to the iodine center, increasing the anionic character of the immediate oxygen. Furthermore, sterically bulky TMP group appears to suppress ligand coupling of bulky tertiary butoxyamide nitrogen during the transition state. When benzoic acid was combined with this hyperbonded iodine compound and treated in the presence of TMP, three-component dihydrative condensation occurs, resulting in the quantitative formation of this TMP iodine benzolate. The resulting salt was subsequently heated in toluene or under solvent-free conditions, leading to ligand coupling and the formation of phenylbenzolate. So we call this stepwise ligand coupling approach. In this approach, ligand coupling rarely occurs in polar solvents due to the ionization of the diaryl iodine salt in the polar solvents. The stepwise ligand coupling approach can be utilized with a range of benzoic acid aliphatic acid. Corresponding allyl esters were produced in satisfactory yields, and the scope of the substrates and functional group is comparable to the phenols and amide coupling reactions that are previously discussed in this lecture. Our stepwise ligand coupling method exhibits a high level of chemoselectivity towards carboxylic acid. For instance, when we apply this method to cholic acid, which features 3 hydroxy groups. We obtained only the ester product without any impact on the hydroxy groups. Conversely, conventional esterification methods often suffer from side reactions involving free hydroxy groups and poor solubility of cholic acid in the solvents. This outcome thus demonstrated the effectiveness of our method for tackling multiple functionalized substrates. Aryl difluoromethyl ketones have been synthesized through transition metal catalysis by reacting bromodifluoroketone with aryl metal species. The combination of aryl halide with difluoroenolates has also been reported. Our stepwise ligand coupling strategy was extended to decarboxylative arylation, resulting in the production of aryl difluoromethyl ketones from TMP adenine difluorobeta kiss acid. The reaction was first monitored by NMR to confirm the ligand exchange at room temperature. Decarboxylative ligand coupling occurs at a temperature of 100 degrees, resulting in the formation of this particular coupling product. On the other hand, free enolates generated from decarboxylation cause the formation of aldol product. In contrast, in the presence of the same aldehyde, our stepwise ligand coupling approach exclusively produces the alylation product without formation of aldol product. Our stepwise ligand coupling approach enables the interaction of aryl groups with varying functionalities, resulting in the successful production of aryl difluoromethyl ketones from this acid. This process represents the first example of decarboxylative alylation using diaryl iodine salts, and our method allows for the synthesis of biologically active compounds from these functionalized products. For example, potassium hydroxide could be employed to remove the aryl carbonyl moiety. Grignard reaction resulted in the formation of a tertiary alcohol. The reaction with MCPBA led to the quantitative formation of this aryl ester, which has subsequently reacted with pyrrolizine to produce the corresponding amides. The AMPA allosteric inhibitor was synthesized using this amide as a key intermediate. In a stepwise ligand coupling approach, boronate anion functions as a good ligand and nucleophile platform for coupling reactions. This stable boronate salt is formed rapidly through ligand exchange, which occurs at room temperature. The nucleophiles on the boron templates demonstrates exclusive reactivity toward aryl groups in the presence of a range of functional groups and electrophiles. For instance, fluoroalkoxyborate could undergo rapid ligand exchange, and at 100 degrees, it produced all arylated product in quantitative yields. We will expand this strategy utilizing a boron atom as a nucleophile platform with the aim of developing a metal-free version of the Suzuki coupling in the near future. So today, I have introduced reactions that enable efficient alylation of nucleophiles using TMP adenine salts in the field of metal-free heteroatom alylations. The ligand of the iodine salts plays a significant role in these reactions, with the TMP group contributing to selective aryl group transfer. Moreover, the synergistic effect of TMP with acetate ligand dramatically improves reactivity by facilitating ligand exchange and ligand coupling, leading to extremely high yields in O-alylation of phenols, N-alylation of alkoxyamines, and O-selective alylation of benzamides, The stepwise ligand coupling approach is effective for allylation of carboxylic acid, resulting in the formation of allyl esters and allyl difluoromethyl ketones after decarboxylation, as well as fluoroalkoxylation using boronate as a nucleophile platform. We believe these examples complement transition metal catalysis as a sustainable synthetic method. However, it is important to finally note stoichiometric amount of this diallyl item salt should be used for these transformations. The goal of metal-free hypervalent iodine coupling is to achieve catalytic reactions, and we have partially realized heteroatom allylation by hypervalent iodine catalysis for CN coupling reactions. So, at this time, I will not discuss this mu oxo catalyst for metal-free allylation of specific amide molecules. This catalyst, in the past decades, the Antochik group and other researchers have made substantial advancement for metal-free CN coupling reactions. So fortunately, our new oxo biallyl catalyst allows for the most hypervalent iodine CN coupling reaction in an efficiently catalytic manner, as detailed in a recent Wiley book chapter. Also, we recently summarized the structural characteristics of hypervalent cyclic compound in Chemical Society review journals. I hope to introduce this new catalyst in the near future. Okay, so this research I presented today is supported by many collaborators, advisors, and effort of these many students. We also acknowledge financial support we have received from the Japanese government and related organizations, as well as a research program at Ritsumeikan University. So this is the final slide. Japan has a significant production of elemental iodine, which has led to a high level of activity in iodine-related research. If you are going to visit Japan, you can easily access our university within a half an hour from Kyoto City, a famous traditional place. Thank you for your kind attention, and thank you for giving me this opportunity to introduce one of the hypervalent iodine chemistries. And if you have any question about my research, feel free to approach me by email. Thank you very much.
Professor Toshifumi Doi, you have shared your wonderful thoughts on metal-free coupling by hypervalent iodine activation strategies of aromatic rings. You have discussed about the hypervalent iodine reagents and their low toxicity, how they are found in abundant, their resources, their green characteristics, and also you have discussed how they show their valuable ionic reactivity due to their high electrophilicity. My sincere thanks for your exceptional thoughts, your insights and expertise made a significant impact on us. Thank you, Professor Doi.
Thank you.
Thank you, sir. We would like to thank you on the behalf of entire Shamla College. Thank you so much, sir, for joining us. Thank you, Pravita ma'am, for the smooth conductance of this thought-provoking and insightful session. Now I request Dr. Raghavendra to present a token of gratitude to Professor Pravita Kumar.
Thank you so much, convener, co-convener, and the whole organizing team.
Ma'am, for
और भी है थैंक यू सो मच Thank you so much, convener, co-convener, whole organizing team, principal, for inviting me to chair this session, and I'm very happy. Thank you so much. Thank you.
We are equally
Thank you,
happy
ma'am.
to
Very
have
happy to
you
see
with
you
us.
here.
So we are equally happy to have you with us. Now, I would also like to thank Dr. Kanika Solanki and Dr. Radhika Gupta for coordinating this session. Our heartfelt gratitude to all the speakers of the session for their enlightening and brainstorming lectures and sparing their valuable time for contributing significantly to our conference. Now, I request all the dignitaries, faculty members, and students to join us for the tea. I request all to gather here within 10 minutes for the next technical session of the day. The chairperson of the next technical session is already there with us. So we'll begin within 10 minutes. Thank you.